second intention to come here to learn about that. And Alan's presentation was a very good first introduction for me to understand these things better. Okay, so I will talk a little bit about the presence of water and ice on Mars, and I will do that in two parts. The first one is more or less to inform about the recent results and the real situation on Mars with respect to the presence of water and ice. And the second part will then go more into this sort of the pre-melting aspects of the interfacial water in the Martian surface. Okay. I should start with a comparison. You know these two planets. Arthur C. Clarke has, I think, correctly mentioned that this is a wrong name. That's the Earth. It should be the name, have the name water, planet water, not planet Earth. Okay, and that's that's Mars, and what we can see here we have a lot of water, of course, but we have also on Mars here in the polar caps and also in the atmosphere we have also water there, but from the biological point of view, unfortunately, not as much water as we have on Earth. But we have water there on Mars and on Earth, and that's, I think, for the first view, it's a surprise. If you try to look back to models of the origin of the planetary system, and in all these approaches in a protoplanetary or preplanetary disk, it's very hot in the inner parts. We have friction, capillary movement, capillary motion more or less, so the velocities are very fast inside and outside. They are slower, so we have friction and we have heating of that disk, and the temperatures, it's model depending, but are here in the inner range of 1,000, 2,000 or Kelvin or more, depending on the model and so on. Okay, in any case, we have a strong temperature gradient and the so-called snow line. That means that line, or that's the distance from where ice is stable in this disk. It's anywhere seen in the present structure of the system in the region between Mars and Jupiter, the snow line. So we haven't had here water in the early preplanetary disk, not in large amounts. The stable water, ice, was existent only outside, and then here we could have had water vapor, but that has also been transported away. So the interesting question is, how did the water come in? I think that's, we know all these speculation that comets have brought in water, or we have very so-called primitive asteroids which have brought in the water. So that's an interesting story, but in any case, if the water came in a second phase of the evolution of the protoplanetary disk, then Mars should have gotten a lot of water. Earth too, Venus too, less, but okay. And we should expect that Mars would have, at least in comparison to Earth, about the same relative amount of water, and it doesn't have that as we think today. But we know there is ice, and mainly in the polar caps, and one should know that we have two types of polar cap. That's a permanent cap we can see here in this darker structures, and this is covered by ice, mainly by CO2 ice in winter time. But that permanent kilometer high structure here, it's enhanced by a factor of 3 to make it more impressive. It's not a real geometry, but nevertheless, this is about 3 kilometers or so. And we have a total volume of water ice about this 10 to the 1 million cubic kilometers, so it's a little bit more than nothing on this northern polar cap. That's water ice mainly, as I have mentioned. Okay, so we have water there and CO2. That means during winter, here we have this permanent, you can see there is this permanent cap. The polar cap can, during cold winter, be covered by CO2 ice to a much larger extent. Okay, so we have permanent caps of ice made of water ice and some cover made of CO2 ice. Here the same number, and, it's about kilometers in thickness. I will come back on a little bit later. The southern cap is a little bit smaller. The reason is, I'll come back to that later on, because the southern summer is warmer due to the inclination of the orbit, and that Mars is during southern summer near to the sun. That's why we have a warmer southern summer, and more water ice is supplemented away, and we have a comparatively smaller southern cap. Okay, here are the structures. We've seen it before, and what's written here is what I have told us before. We have the permanent cap, and we have the CO2 ice, the dry ice covered, and also a water ice covered polar cap. This, it's more or less a repetition of what to bring in mind again is that we have such thick caps that what might be of relevance in view of pressure and so on in sub internal dynamics. And if you take all the polar ice melted on the surface on the planet, we would have an ocean about 11 meters deep. So if compared to Earth, it's not so much water there, but there is water in the planet. And there's one completely unknown thing. We know we can estimate the water ice content in the polar caps, but we have not real measurements, really seriously estimate that amount of water which is deep in the surface, also at mid-latitudes and in the equatorial latitudes. That's a yet open question. Coming back here to the caps, this is a southern, this is a result of the Omega mission. The white one is CO2, the dry ice, and the blue here at the warmer outskirts, so to say, is our signs for water ice. So both water ice and CO2 ice are in these caps, and that's a very interesting structure. And in the smaller scales, to see that we have areas with neighboring, like Swiss cheese, of CO2 ice and of water ice. Okay, and this view on the polar caps and the depths, it has been, we know it better now since we have these Charad results radar observations, also by a former ESA mission, that we see here the deep into the surface. That is the orbit projection onto the surface, and you will see here the height scale of the southern polar cap in that case. Southern northern polar cap, so in this is a scale of 1 kilometer, so that's 2 kilometers and more in depth. So that is a state of art. We know about the polar caps, but we know there is more water on Mars. There's also water in the atmosphere, and during very cool night times we have saturation in the atmosphere, so we have also on the cold surface and frost phenomena. You see, it's not a large amount of water, but there is also water in the atmosphere which can be followed by frost on the surface. In a more recent picture to demonstrate that this is from Opportunity. There's a calibration surface, and what we can see here is in the morning hours we have frost also frozen there on that structure, and it becomes warmer a few hours later in the morning. Then this frost, of course, is supplemented away. So water is a constituent of the Martian atmosphere and interacting with the surface of Mars. And then let's come back to, or let's go to the question, what was the hypothetical content of water of early Mars? Probably you have already seen some very optimistic artists' concepts, designs, taking or assuming something like a northern ocean. That this is a northern ocean is simply, here we have a molar picture of the height of the topography of the Martian surface. Here these high mountains, Olympus Mountains, 24 kilometers height, and here the bluer color, these lowlands, the northern lowlands, here these impact basins, Hellas and Agyra, which are very deep. But most of the northern surface seems to be very young, no crater as I see in the southern hemisphere, and it's rather large. That's about 20 kilometers, 24 kilometers. That's about -10 or so in the height. And of course, if we have had water there, then we can assume that it has mainly been accumulated in the northern ocean, so to say. But that is a speculation, but we have increasing evidence that indeed there has been a lot of water in the northern hemisphere. This is, for instance, assuming 3 different depths of water in the northern hemisphere, the water ocean, and you see the corresponding coastlines, and it's very difficult to identify these coastlines, these hypothetical coastlines with real features. But some of the morphologists, geomorphologists think that they can identify at least parts of that temporary coastlines. And another indication that we have had really a lot of water in an early Mars are these structures, these terrace-like structures, which are explained by the geomorphologists by the gradual sinking of the water level during the Martian evolution. And another hint, I think is well known already since Viking times, is that we have dendritic structures on the surface, which can be seen also present yet, and these are also indications for maybe for water.
Can I ask something really?
Yeah.
On Earth, I thought that the sedimentary rocks in oceans form because you have things living there which have shells, and these die and it falls down and form rocks. So is that saying that there was life in these oceans on Mars?
So far as I know, that is working also without life. That sedimentation process.
Okay.
So I think that cannot be used as a proof or a strong indication of life, of relicts or so. Okay, so another aspect which is more of interest in this community is that we also see traces, polygons on the Martian surface, which are very similar to permafrost structures as you see them on Earth, what indicates that we will have had also periods when we have a wetted surface which will have freezing and then thawing, and again has formed such structures. Okay, and another aspect is
at what latitude do those permafrost layers appear on Mars?
At mid and higher latitudes. I don't know if there are also sites at equatorial latitudes. I don't know. I haven't looked for it, but the observations I know are from mid 30-degree and higher latitudes. Okay, another aspect is here we have this sediment parts, and what can be seen here is also some gray blue spheres, so-called blueberries, which are seen better in this image, and which are understood as to be originated, to be caused, or to have evolved in a watery solution. So they are also indications for earlier lakes. That all is evidence that we really have had water in the early Mars more than today. The question is, where did the water go? Of course, one way out is dissociation in the atmosphere, H2, and is leaving into the space. We have had, if we have had a Martian magnetic field, a global one, then we know that it has existed before about 3.9 billion years. So most of the time Mars has had that magnetic or magnetospheric shield, and the ionosphere can leave the ions by the solar wind. and that is one loss mechanism mainly for hydrogen. For oxygen, it's a question where it has gone then, maybe in the highly oxidized surface as we know it today. Okay, the old class, or the former class, pre-omega I should say, what I show here is also derived from omega results. The old classification of the evolution of Mars was in these three phases, in Archean, Hesperian, and Emersonian, and that was based mainly on crater statistics and rated into that areas on Mars they refer to in that aging classification. We have now some more detailed knowledge in that sense that we know that we have locations for clays, sites for clays on the surface, and can relate them to the age of that surface. Then we have a sulfate dominate area have had, and now what's that?
Let's move it maybe.
Oh,
No.
oh, here it also doesn't work. I see.
Oh, yeah.
No,
No, that's what it is, yeah.
no, it's again.
Hmm?
It should come. Here it is. Yeah. No.
So just to
Sorry.
ask, so the clays and sulfates and all this, is it observed remotely?
This is Omega has had spectrometers on board, and so by spectral classification they have identified minerals, different types of minerals, and have related them to the age of that area. And one can see that indeed we have in very early times have had clays indicating presence of water.
And the ages are coming from the meteorite data? Or
Yeah, from cratering.
Okay.
From cratering statistical meteorites in that sense. A little bit larger meteorites to make craters. And what you see is that in the first half a billion year or whatever, we have had water-dominated processes on the surface. And then that has been a very interesting phase on Mars. As I've mentioned, according to models, we know we have some local magnetization on the surface of Mars, local anomalies, and all these investigations indicate that a possible global dipole, for instance, it should probably have existed, but it died at about 3.9 billion years ago. On the other side, these high craters I have shown before, that area, the Tarsus area, has probably evolved also during that time, 3.8, 3.9. So it might be that strong volcanism giving sulfur into the atmosphere and the surface has at that time essentially changed the complete surface, the complete evolution of Mars. Until that time, about 3.9 I thought, it has been probably more or less similar to Earth. We have had water, warmer conditions, and more or less terrestrial-like conditions. And if we speak about life on Mars, or think about that, then it should have evolved, originated in that time, in this first half a billion years. Later conditions are, to our understanding of life, to what we know is life, that are very bad during that later phase, and also the current. We have now the current phase that we have more or less anhydrous ferric oxide. So if life has originated on Mars, it should have happened in that earlier time. So the question is, in view of Mars, of life on Mars, the first is, have we had life on Mars? And then we have to look for traces of that also, which might be in the surface. And the second question is life really so capable to adapt to such changing conditions that it may have adapted or to be present? That is the two questions with respect to life on Mars. But the precondition is that it has originated in that first phase of 500 million years. It's more or less the same 500 million year we assume for Earth, when life has started to be active on Earth. Okay, so that is the view of the evolution of the surface of Mars. And coming back to the present situation, as I mentioned before, we have an inclination of the rotation axis more or less similar to Earth, and Mars, or the orbit of Mars is much more eccentric than that of Earth, so we have a great difference between north and summer and then north and winter, for instance, southern summer and southern winter. Here we have southern summer. You see it is very near aphelion conditions, near to the sun, but of course the velocity is larger here, and we have an eccentric orbit, so that is a shorter time. We have a warmer southern summer. And I should mention that during that warmer southern summer, the surface temperatures can reach here in that area about 20 degrees centigrade. That means if you have a good vine plant, you could go there for summer conditions, but they are very short, and I think it will not be a good wine. But nevertheless, it is plus 20 centigrade under best wine conditions on Mars. Okay, then you see the winter is cool and longer, but more distant from the sun, and that makes a difference between the northern and northern and southern seasons. But I have mentioned we have some water in the atmosphere, also present, and that is normally described in so-called perceptible micrometers. That means if all the water content in an atmospheric column is condensed to that ocean below, then the height of that ocean can be measured in micrometers. This is the 10, 20, 30 micrometers we have. Of course, here in the polar regions it can be much more, but for normal equatorial mid-latitude conditions we have several 10 micrometers, perceptible micrometers. This is an older view from, and this is a more recent description of that situation. The main change is, I think, that the modern presentations are in color and they are in lines, but the content is more or less the same. You see here up to 40 or more at polar latitudes, and the blue in that area. So for model calculations, normally 10 perceptible micrometers are taken as a numerical example. And when speaking about that, the presence of water on Mars, I think in the atmosphere, one should take this into consideration. That phase diagram. Here is the water. Okay, here we have liquid, vapor, and solid, and flow. We are just in the range between solid and vapor. That means we have sublimation, resublimation as the main process in the upper surface atmosphere interaction. And here is that corresponding pressure for 10 perceptible micrometers and for 100 perceptible micrometers. That means we are here in that 200 K about as an average temperature in that range for the Martian PT conditions. And it's quite clear that bulk water does not exist at that temperatures. That's, I think, clear to everybody. We have no bulk liquid water under the present conditions on Mars. The other question is, okay, no bulk water, but we have ice. Can we have ice in the subsurface? If you assume we have had much more water in the atmosphere and on the surface of the planet, then the planet cooled down, we have had ice. What happens with the ice under that thermal conditions we have? It should sublimate, and then you can make estimates how much of the upper part of that ice in the surface has been sublimated away during the evolution of Mars. And it depends, of course, on the diffusion, the possibility for diffusion of the water vapor if it has been sublimated to go through the surface and to leave the surface. Here's the water for core pore diameter for diffusion of about 1 micrometer, and this is 10 micrometers pore size. And you see, depending on latitude, here this is equatorial latitude, this is polar latitude. It's no take into account north-south azimuth, it's average conditions, equatorial conditions, polar conditions. And you can see for the different ages of 2.8 billion, 4.5 billion in current conditions, the depths of the dry layer above the not yet supplemented ice. And you see that these calculations indicate for equatorial conditions about 100 meters or so, the depths of dry soil above the ice if it has existed there. And if you go, of course, to the polar, that you can reach much lower thicknesses. That is described in the same way here by coding. But of course, you can see that if you have much porous, more larger pores, then the curve is a little bit changed, and we have the ice horizon at much deeper layers. That is also the current question: how deep is, depending on the local conditions, the water content. But we have seen it was 10 meters, 100 meters or so depth, and it was a great surprise. And Mars Odyssey came out with the results. It has been already mentioned before that we have indeed also at mid-latitudes some large areas with a high hydrogen or water content. It's up to 10% or more. This 80% is a little very optimistic, but nevertheless, in this method, the neutron scattering works only for depths down to about 70 centimeters, or let's say 1 meter. That means we have this water content in the region of 10% or so in the upper meter. That is what was quite a surprise, because if, according to normal conditions, as described before, all that should have been supplemented away. But we have really on present Mars some areas with a comparatively high water content in the soil. That means weight of the water compared to the weight of the dry soil mass in the range of 10% in this area. And it's not yet clearly understood now what is the reason for that, but we have to see that there is indeed also at mid-latitudes, which should be dry, in the upper meter there is a lot of 10% of water on Mars. If one compares that with the conditions to have bulk water also, Haberle and others have made some estimates looking for conditions when we are in PT above the triple point. And the numbers, which can be seen here, they are in the range of 4, 5, 9, or 10 in that area of these lines. They indicate the days in the Martian year. During that, the conditions are given that we are on specific locations temporarily above the triple point. This is the Hellas Basin, for instance. I have shown you this very low, and therefore, yeah.
Sorry, that's for that 10 to 100 precipitable micrometers.
Yeah, for 10.
So.
And so most of these model calculations are made for exemplarily 10 precipitable micrometers.
Yeah, I guess on the space diagram it looked like you would never get there as you went higher.
Yeah, and high altitudes change. I will come back on it. Okay, we see there are some preferred sites where there could be these conditions given to be above the triple point to have liquid water on the surface, but we will see that that's how it works. If you compare that to topography, you see that of course is Hellas Basin. Of course, it's very deep, and that's why we have a higher pressure, and we are more longer times under these conditions. But we do not see any correlation. For instance, we see some correlation with these outflow areas here, but we do not see really correlations with the Odyssey observations. Here we have these Odyssey observations. We do not, it should be here anyway. We do not see real coincidence with that.
So what's the highest pressure you get at the deepest basins on Mars?
Water really low.
But it's I guess, so are they calculating it with, instead of the partial pressure, they're taking the total pressure of the atmosphere? Or?
They all have taken the total pressure, of course,
Okay. Yeah.
to study or determine the triple point. Yeah. Okay. So that remains an open question. How can that be related to the surface properties and into the evolution of Mars? But we can say there is also in the upper meters, in several but large areas, in low and mid latitudes, rather high, 10% of the content of water. And if we have water there, then of course there is a question what can be the consequences of that water. Physical consequence one could be indicated here, and I hope that there can be relations to your work, the dynamical consequences of pre-melting. There are a lot of examples in the slope of a crater. During spring, we see such phenomena which suggest something like a flow or a rheological process. There comes something out here which is dark and which is transported downward. This is not what is also often seen in the literature. These CO2 geysers, for instance, which are assumed to be also to happen during spring, and which are geyser-like outflows of CO2 blown by the wind, and you see the traces then, straight traces following the wind, and you see the deposition then of the dark matter. This is not wind blown here. This is really gives the impression of really something like a flow process. So that are current indications of water at present in the upper surface of Mars, upper surface of Mars. And we have another indication for probably water-caused modifications. We see here, it was in August 99, and this is September 25, 2005. So it's 5 or 6 years. And you see here, as you can see nothing. And here you see this new deposit, which might be more or less dry, maybe caused by water or not. There are different approaches to try to understand it, but it's also, I think, a challenge to these pre-melting aspects. And we have more or less similar image from Phoenix, indicating also that we have indeed water on Mars, but the main information is in this between two is this is an earlier image, and this is assumed to be ice, really water ice, and you see that sublimation has reduced that appearance of the water ice. So we have seen by Phoenix really sublimation, results of sublimation on the current Mars, but it's about 68 northern latitude. So it's a very cold region, but nevertheless, the main result is that when we have in the upper subsurface, it's about 5 centimeters, we have in these upper parts of the surface, we have a cover by dry material, and then more below in the surface, we have really existing ice, which sublimates away and can be followed in the evolution or in time. Another very interesting aspect, also related, I think, to these pre-melting aspects, is that we have in the vicinity of Phoenix, you can see some polygon-like structures here in the meter scales also, not the large one as I have shown them before, which are 100 meters or larger, but on these small scales there seems to be something like this polygonal structure in the surface. And yeah, so, and this is the last Phoenix image seat just below the station, and during the landing by an active propulsion motor, not simply falling down as the former missions. And we have had a rocket engine to stop the falling, and that has blown away the surface, or at that side where the landing took part. And we really see here naked or blank ice on the surface just below the lander. So that is, so to say, a first direct image of water ice on Mars, and there are also indications that I will mention that later on, that when handling the how to call it, the arm or phoenix, and digging, then and making some ice free, then indeed the water content of the atmosphere increases. Okay, but as a first summary, what we know is now, first there is water on Mars, and mainly in the atmosphere, and as ice in the surface. And there is no stable liquid bulk water at the Martian surface. Nevertheless, and that will be then the second part of my presentation, I will discuss that we may have, or will have, I think, undercooled liquid interfacial water melting as the background physics can explain that appearance, and that is in the subsurface of Mars, means within the grains, or the mixture of grains and ice. And of course, we have no bulk water, but we have liquid interfacial water, at least temporarily in the surface, and that of course will have consequences, physical. I have mentioned shortly, neurological, for instance. We have chemical consequences, I will discuss it later. And if you have chemistry, it's not forbidden to think also on biochemistry and to think about life. And I think, to my view, it's a real challenge, current challenge, to study the physical, chemical, and biological relevance of this undercooled liquid interfacial water. So I will mention some aspects that's all in this first part, and I will discuss that more in detail in the second part.
Okay, so there we have plenty of time for discussions and questions. Yes?
Yeah, this great climate change, is it by coincidence that it coincides approximately with the late heavy bombardment on the moon? Has there been some kind of studies coupling the two?
I think the answer can be also some information from the field speculations. There are different approaches. But one should be careful, I should say that first, with this heavy bombardment. We know that, and there is thinking in two lines. One is that we have, normally the decrease in a smaller body because they are captured by a larger surface in the late phases of the protoplanetary disk. Then, of course, the larger bodies accumulate all the smaller ones, and that decreases. So, was that the late bombardment the last phase of that declining activity, or has there been really one special event which has caused some additional things? And we really do not know. Has happened there something in the asteroid belt, collision of two larger one, which gave reason for such bombardment. But nevertheless, it keys that stopped at about 3.9, or was going down to the current level of very comparatively very low impacts. If these impacts have had a role, then there are some approaches, or some speculations, that we may have had a very large northern impact. we have seen in the northern hemisphere is quite different in its properties. It's smooth, no crater. So that has been altered by such a large impact. If that has happened, but we have seen that the water was already before, then of course it should have had a strong influence on the internal dynamics of Mars, and it may have caused also the volcanism which starts at that. But it may, and we do not know really what it is, so it is speculation. But so the reasons, to my knowledge, are not well known, and we have not solid answer. But there has happened something really which has influenced the internal dynamics, magnetic field of Mars, and also the surface around half a billion years after formation of Mars. But we have no serious model what has happened there.
Well, I mean, if the dynamo turns off, then you expose the atmosphere to solar wind, and then you can start to lose material out of the atmosphere. But I don't know whether that's the actual model of what happens. I can't remember.
Yeah, I think you're right. When we have stop of dynamo action, solar wind has excess, and from that on we have quite different interaction of the atmosphere with space, so using the volatiles in the atmosphere, and that changed the atmosphere, of course. That period started at about 4 billion years ago. But why, really, we can speculate. It's sometimes more interesting than okay.
From the exploration side of this, which I'm ignorant, what probes are available in principle, or have been available, to distinguish the phase fraction as a function of depth, even in the top meters? On Earth, we could use multiple wavelengths of various types of electromagnetic radiation to look at the phase fraction, but of course you're limited in what you can deliver. Is there multiple wavelengths of radar that allows one to? I mean, you made the strong statement there's no liquid water on the surface, which seems eminently realistic and true. But then the question would be, can you see deeper? And some of those features you showed us, I know people have speculated there are actually some outflows of liquid in various things.
I could formulate the answer in an unexpected way. I think that is a call to apply geophysical methods to Mars in future missions. The start was, we had 2 radar missions which looked into the surface. That was Mars's on the ESA mission Mars Express, which gave results, and we got better results by this charade I have shown on the NASA mission. So that were, I think, the first real look down into the surface. What is planned, to my knowledge, is, for instance, with ExoMars, that's a mission planned by ESA, start 2013, launch 2014, that will have digging about 2 meters to position their device to measure what has been mentioned today before. We have speculation about this 20 milliwatt or so per square meter of the heat flow from inside to measure that. That is the first try to get more solid numbers than that, which are more or less speculation. So that is another physical. What we have done with Phoenix, for instance, is this TECD instrument measuring electric currents in the upper surface. And the outcome was that they didn't measure them because there was not enough water in the part. I will come back in the second part on it. So that I am aware of. And also MSL, the Mars Science Laboratory by NASA, launched 2009, will have some geophysical instruments to look into the upper parts, decimeters of the surface. And the deeper measurements have been made only until now by radar.
But those pictures that both you and Alan showed of the Phoenix lander exposing this ice,
Yeah.
was that a surprise that it was so close to the surface?
Yeah. Yeah, that it was only 5 centimeters or so of the dry soil. That number was unexpected. It was hoped for, but it could have maybe we were lucky, or Phoenix were lucky that if going 100 meters away, it could be a meter or so. So we do not know how representative that is. But of course, they were very glad to have sit down just on that side.
Has there been, I mean, from orbit, is a radar instruments able to see any depth? I mean, if you have such a thin atmosphere, you would think that with radar, you would have, the atmosphere shouldn't be too much of a problem. And on Earth, we use that for probing the thickness of glaciers, for example, but also in ground penetrating radar, where low electrical conductivity is just what you want for that.
Ground penetrating radar is foreseen to be mounted on ExoMars, as I have mentioned, and also on MSL. That is planned.
So they should be able to see more than decimeters, I would have thought.
They are for 10 meters or
10
whatever.
meters, that's what
Coming back to the assumption that if you lose the dynamo, you're done, you're toast. What's the initial value problem for this planet? I mean, has anyone said anything quantitative about how you might have started and what the dynamo might look like, and what the time scale of a dynamo, the loss of the dynamo would be? Because we know it would be disastrous here on Earth. It's obviously maintained itself, and has anyone made that estimate?
I know only speculations which assume a sharp stop, maybe by some changes in the internal dynamics or so, maybe caused by impact or whatever. So the only what we really know is that we have the magnetic anomalies, locally very strong magnetic fields, much stronger than we have on the surface of Earth, 10 times stronger on the surface. 400 nanotesla, I think, or more. So that is what we need. And what we also know is that they have surprising similarity to what we see, for instance, in the Atlantic, which these parallel stripes, plus minus, or in the sense of inward or outward directed magnetic fields. That's what we know really. And that is remnant magnetization of the surface material, and so it gives some limit or some orientation for the strength of that early dynamo. But about the time behavior, we know only that stripes which fit into that first half a billion years, no more.
Yeah, I mean, there's been a little bit of work done on this. However, this recent idea that the difference in the thickness of Mars's crust may be due to a giant impact at the surface, that will certainly sort of mess with the internal heat transport processes in Mars. And so if you have a field being generated within Mars at the time of that impact, that could disturb it. And what that does to the convection in the mantle, which is sucking heat out of the core, that's not really well understood yet. There are some people that are working on that just in the last 1 or 2 years. But I don't know, maybe Axel knows, but I don't know how much stuff has been done on.
Yeah, there was a talk by Catherine Johnson recently, and from JPL, and they looked at this. And indeed, so they're thinking that perhaps an impact could have heated the outer parts so much that the tiny little bit of heat difference, or temperature difference that you need in order to keep the thing running, is just decreased below critical, and then it turns off. The typical decay times are short. So by short, I mean 1,000 years at most.
Those sort of impacts didn't happen here on Earth?
No, they did. That's why we have our moon.
Yeah, but that's my theory, about the. I'm not informed in these things, but the question is then why it didn't happen that with the dynamo on Earth?
By the first time we didn't go off, you mean?
Yeah.
Well, I mean, what happened
Nothing
during the
enough, big enough or so.
Yeah, I mean, in the moon forming impact, if you had a dynamo before the impact, it certainly would have been, reset or whatever during the moon forming impact, because you actually bury the core of the impactor merges with the iron core of the Earth, and that core from the impactor is screaming hot, and so you would completely melt the core of the Earth during that event. So whatever, it's a large enough impact that it completely resets the heat transfer problem, in the Earth, and you have to basically start again from zero with a planet that's heated from the outside from its impact, as opposed to heat from within and losing heat convectively to the surface. Oh, that's like nothing. The moon forming impact was something the size of Mars hitting the Earth, and KT was, tens
So
of
that's
kilometers.
completely settled. There was an impact formation of the moon.
More or less. Yeah.
The last time
It's not 100%, I'd say 90%.
The current view, yeah. But I should mention in that context, it's interesting to see that our dynamo produces a magnetic dipole which is inclined to the axis of rotation. It might be also one of the expectations that may be caused by that impact, changing the internal geometries, shifting the activity, having two axes now.
Is it? I mean, I was under the understanding that the actual the date at which we developed our solid core was still something that people argued about actively.
Yeah.
And sort of around the time of the moon forming event, we may or may not have had a solid core at that time, in which case, solid inner core.
Oh.
And in which case, the style of convection. I mean, there has been this view that what gives us our dipole is these Taylor columns that are forced into existence by the formation by the solid core. So the style of convection is controlled by that. Now, recently there's been a paper claiming that that's not true. There's some supercomputer simulations by the people in Japan that were published in Nature within the last couple of months that were looking at higher resolution, and those Taylor columns all disappeared. So I think that some of these things are still open as far as
Well, I mean, the Earth was certainly differentiated when the impact happened.
Differentiated,
but
then
not
the question
necessarily
of
with the solid core.
with the solid core. How important is the solid core for the style of millennium of the dipole or not? I'm not sure that that's determined. I mean, there was this Taylor column idea, but.
Well, you have, of course, both effects working: compositional convection and thermal convection. If you don't have the inner core, you probably don't have this compositional convection yet, and it's all governed by thermal convection. But as long as there is some convection, it's okay. You will run a dynamo regardless of whether you have a core or not. In both cases, it will work. There are also stars which are fully convective, so the presence of a core is not really critical.
But the time scale for flipping and everything else changes.
It may, it could have been more stable perhaps in the absence of the core. So that you would have more stable dipole that wouldn't have reverse, perhaps. But these calculations of reversals are also not really very certain. I mean, they get reversals, but if they change certain parameters, which should be asymptotic anyway, and things still change, and they get longer reversal intervals. So that's not very clear.
And first real measurements of current heat flow, we need that to model that models will hopefully then come from that mass, from the exomark measurement, the heat flux device.
Yes, shall we close for lunch and thank both speakers of this morning's session?